Hello, this video is entitled Surface Integrals Non-Parameterized. And what that means is surface integrals can be handled two ways by using parameterization techniques, hard word to say, that are learned in the previous section that I'm not covering. So therefore, to cover this section, all I have to do is just eliminate those type of problems and only focus on them in this form, and not parameterizing them. So if you're looking at whatever book you're using, if they use anything that looks different than what I'm doing, it might be using a parameterized version. Essentially, well, the main reason for this is I wanted to kind of get through the course content as quickly as possible, because I want to get to the Stokes theorem and anything I can sort of kind of eliminate from a time standpoint, because that won't even be relevant for the next two sections after this. So it would have only been used here. So I just saved a full section of notes plus part of this. So let us begin. I'm going to scroll down for a second and kind of show you. We've talked about line integrals. And surface, it says, relies on splitting the surface into small surface elements. So you're kind of integrating on a surface element, kind of map down onto whatever your region is here. You map it down, you're integrating along that path. Hard to explain the visual part of it. So they're small, little infinitesimal surface elements. So I don't know if these pictures help, but that's okay. So to evaluate the surface integral, we use the following integral. Double integral of f of xy, and g of xy is basically just z here. So if g is a function of xy, and we're integrating over the surface integral of f over s, whatever the region s is, which is kind of defined by this. 1 plus the g partial squared, gx partial squared, plus the gy partial squared, then dA. So in other words, whatever, either dy dx, dx dy, or polar, r dr d theta. So actually I'm mentioning right here, if f of x, y, z equaled 1, if that part right there equaled 1, this would just be the formula of the surface area that we learned in the multiple integration section. Except that we're using f there and not g. And then I'm mentioning here, finding the mass of a surface lamina, flow of fluid through a surface, flux integral, are two applications of surface integrals. I'm sure there's many more. So as we're talking about, dA is integral across the area on the plane, and then ds is the surface itself. It can be curved or plane. So ds means area across the surface, which this radical teamed up with that dA all makes up the ds. So this being a double integral, we're going to have to get this simplified down only into two variables. So we'll see how that's going to work. And here's a couple of modifications to the formula that I don't think you're going to need to make, but well, just in case. But it is possible, if it's projecting on different planes, it's two variables. Normally you think x and y, but in theory you can integrate, it could be xz as a double integral or yz as a double integral, as long as it's only down to two variables. So you see here's an x and a z, and g is a function of xz. And here g is a function of yz replacing x, and then your variables would just be y and z. So that's really all that's saying. This won't be too bad once we get into it here. Mainly, if you can handle these problems that are in my notes here, and then I guess whatever I put, I think they're very similar to the ones I put on the quiz, and then whatever I would put on the final would also be similar to that. I'm not getting very creative here in these last three sections. I just kind of want to show you the basics and not use too much imagination. And I'm sure, which hopefully you'll appreciate, since it gets a little tiring by the time you get to the end of a course. So with that being said, Let's look at this example where surface is a plane, x plus y plus z equals 4. Above a rectangle given as follows. And then the function is f of x, y, z equals 4z. So let's take a look at what we have to do here. Yes, I just replace this, g of x, g of y, same thing as zx, zy. So what we need to do on our region is solve for z in terms of x and y. Like I've done right here, we're going to reverse this to x and y. So that's the g. In other words, the surface is the g. And the function you're integrating across here is the f. So that's 4z represents this part right here. So then if, from x plus y plus z equals 4, we have z equals 4 minus x minus y. And let's take both partials. Now this one's kind of nice and easy here because you get a -1 and a -1. So to fill out that radical, you basically just have 1 plus 1 plus 1, square root of 3. So now I'm going to go with x and y as our variables to integrate here. So now we're looking at basically this function right here. So your fxyz is 4z, and the square root of 3 from right here, and then dA, which we can then determine. Well, I pulled out the 4 and the square root of 3, and then here we know that z is a function of x and y on our surface. So all we have to do is replace z here with 4 minus x minus y, and then I'll go dy dx, and because this is a rectangle, both regions of integration will be numerical. There's no variable here on the inside. So this should work out nice and neat. Let me just scroll back up and let you look at the, see there's the regions. Y goes 0 to 2, x goes 0 to 3. So there was really no advantage on the order of integration on this one, really, since it's numerical. You could switch the 2 and 3, switch the x and the y. All right, so let's just kind of plug and chug through here. And when you get down to one variable, you can use the numerical integration capabilities of the calculator. So antiderivative with respect to y will be 4y minus xy, and then minus 1/2 y squared right here. So I'll plug in 2, plug in 0. And then I plugged in 0 won't amount to anything, but if I plug in 2 for y, that'll be 8, and 1/2 y squared will be 2, so 8 minus 2 is the 6, and then put in 2 right here for y, so it makes it minus 2x. So this is how I got the 6 minus 2x. And of course we still have our 4 square root of 3 hanging on, and now we're basically home free. The antiderivative of this will be 6x minus 2x will be x squared, 0 to 3. Plug in 3, plug in 0, you'll get 9 right here. So if you multiply that out, you'll get 36 square root of 3. And look at what we have right there. 36 square root of 3. Now we have a cone. 5 times the square root of x squared plus y squared. Z is from 0 to 1. And then f of xyz equals z minus y. So let's see what we're going to do with that then. So we have to take the partial derivatives of this z with respect to x and y of the surface. Of course, that's x squared plus y squared to the 1/2. So you bring the 1/2 down and make it 5/2. And then the 2x comes from the derivative of the inside with respect to x. Usually I put that at the end, but I guess I chose to put it first here. It doesn't matter mathematically. And then when you subtract 1 from the exponent, it becomes to the negative 1/2. So then the only difference between when you take this with respect to y, the only difference is it's 2y here instead of 2x. Now this looks kind of ugly, but it's actually going to tidy up real nice. Really nice. I mean, so I'm putting the square of each of these partials into this formula right here. So that looks terrible. Watch what happens. Now, what I did is I looked at this immediately. I kind of probably skipped a step here, but I'll tell you what I did. When you square that denominator, it's just going to be x squared plus y squared because the 1/2 will be gone. Same thing here. So I decided, well, let's get a common denominator. That's probably going to be a good way to do this. So I rewrote 1 as just x squared plus y squared over x squared plus y squared. And then these two terms can be put together in the same numerator because they now have the same denominator. So 5x all squared makes 25x squared. And then 5y squared equals 25y squared. And you can add up that entire numerator. It's going to give you a 26x squared plus 26y squared. You factor out a 26, and then the x squared plus y squareds cancel. So all that mess just simplifies into the square root of 26. That's just fantastic. So now we are integrating right here our function z minus y square root of 26, the dA. All right. So we know that z, the cone, is 5 the square root of x squared plus y squared. Then we just leave this as y because we're just getting this into x's and y's now. So anything that's a z just needs to be moved into x's and y's. So that's our original cone definition. So, all right, this looks kind of messy here, but kind of ugly. But the square root of x squared plus y squared pretty much indicates we've got to use polar here. So the square root of x squared plus y squared is going to be r. And then y would be r sine theta. And then we have the square root of 26, which I can toss to the outside, r dr d theta. Now, what I'm showing you here is how to get the limits of integration for r. Because this 5 times the square root of x squared plus y squared really is 5r. Probably should have written this a little bit differently. And this is correct what I'm doing, but I substituted, I'll just follow this, and I put this in there, I divided both sides by 5. So I have the square root of x squared plus y squared is between 0 and 1/5, therefore r is between 0 and 1/5. And because there's no other restrictions on theta, you may assume it's 0 to 2 pi, which it is. So getting the r there could have been a little tricky, but other than that, not bad. But that's how we would have extracted the r out of that thing. So what I do here, looks like I'll put my square root of 26 out there. Now this, I factor an r out of here and then combined it with that r to make it r squared. So the 5 minus sine theta will just sit here while I integrate r squared, which will be 1/3 r cubed. Plug in 1/5, plug in 0. So you end up with, you can do the arithmetic on that, you just end up with 375 on the bottom of that fraction on the outside. Well, you don't have to put in the outside, but I would. Now we just integrate 5 minus sine theta d theta. So that will be 5 theta plus cos theta from 0 to 2 pi. I guess technically, let me explain this. I see sort of a little mistake. Well, not really a mistake, but improper form. This fraction right here should have been sitting next to this right here, but okay. See, I brought it back over here, right there, and it's in the answer. Just should have put it right there. Okay, sorry about that. Anyway, put in 2 theta, that'll be 10 theta. Cos of 2 theta will be 1. Put in 0, you'll get 0 plus 1. So essentially, you'll have 2 theta. I didn't write all that out, but you'll have 2 theta plus 1, and then minus 1. So the 1s will cancel. I'm 10 theta, excuse me, not 2 theta, 10 theta, because you're multiplying it by 5. So I basically have 10 theta times what I already had right there. And this, you can reduce this by 5 if you want to. It's not wrong if you don't. But it's 2 square root of 26 pi divided by 75. Was that one that already had an answer in it there too? There it is. All right. We have a hemisphere. So essentially, where z is greater than or equal to 0, that's the same thing. So know what you saw for z. They could have written it in terms of z, but they didn't. They decided to give us a little challenge. it would be solving for z, but only taking the positive square root of it, because we're only looking at the upper half of the sphere. So essentially that would have been the same thing as had they given us z equals the square root of 9 minus x squared minus y squared. Same thing, which is the way I wrote it right here. I just didn't use a radical, but... All right, let's take our two partials. So the derivative of the inside here is going to be negative 2x, and that will become negative 1/2 when you subtract 1. This will be negative 2y, also negative 1/2. 2's cancel. So it looks very similar to that problem I did, was the last one, I think. Or let me see. So I want to make sure I don't say it was too many. Yeah, this up here. Looks like it's going to simplify similar to that. So after I didn't show the squaring of this, but when you square this, you're going to have x squared over the exponent goes away on the bottom. This one you'll have y squared over the exponent going away. So I got a common denominator again for this one, for the 1. Combined all that together, and actually the x squareds plus 9 squareds cancel. So it just leaves 9 on top over 9 minus x squared minus y squared. So now is a good time to convert this to polar. So 9 minus x squared minus y squared is the same thing as 9 minus r squared. And then now has a 3 on top, though, because the square root of 9 is 3. So this radical converted to polar is 3 over the square root of 9 minus r squared. That makes... So z squared equals 9 minus x squared minus y squared. So we have that. And let's come down here to our integral. And sort of the reason why I did this, because actually z squared is the function that we're integrating. So that's what that belongs to, converting this to polar right here. I know it's kind of just, there's a z squared here and there's a z squared there. So we're already done with this first z squared. So we took care of that right here when we solve for that. But we do have the fact that z squared from the surface region is 9 minus r squared times the region of integration. I mean, that's the function, excuse me. This is the surface part. I got that backwards. This is the surface region right here. That's just the function you're integrating. And then r d theta, don't forget our extra r there, and we're going from 0 to radius 3, and then 0 to 2 pi. Because that sphere would have a radius, our hemisphere in this case, would have a radius 3. Okie doke. Now this will probably simplify a little bit. Sure enough it does. We have 3 times the square root of 9 minus r squared, r d theta. Well, if it wasn't for that r, which obviously has to be there, so we didn't just put it there for no reason, but that r is our friend here, because we can use U substitution instead of like trig substitution, because that integral would be trig substitution if it didn't have that r there. But now it's just U substitution. So let's come down here and do a basic U substitution. So let u equals 9 minus r squared. Du would be negative 2r dr. Negative 1/2 du equals r dr. U of 3 equals 0. U of 0 equals 9. Alrighty. So the negative 1/2 comes out here with that 3. I'm going 0 to 2 pi. Now I'm going 0 to 9. Now, one thing you could have done here is I didn't choose to do it. I could have used that property from definite integrals in Cal 1 where I could have gotten rid of this negative. And see, this is right, 0 and 9, the way this is written here. I could have flipped those over and got rid of that negative if I wanted to, but I didn't have to. Now, one thing about this, and I'm sure I mentioned this back in the double integral videos, is that it's different now than it was in Cal 1 because you have more than one integral, or even Cal 2. You don't flip both of them. You can only flip one of them to get rid of your negative. But anyway, that's all right. So the antiderivative of u to the 1/2 is 2/3 u to the 3/2 from 0 to 9. So that completely cancels out except for the negative. So I have the negative of 0, 9 to the 3 halves is 27. So I have the negative of negative 27, which of course will be 27. And now I go 0 to 2 pi d theta. So I just didn't bother to write theta down there, but all that does is bring a theta in there. So you have 27 times 2 pi, which is 54 pi. Look at us go here. All right. Have another one here. Here's a cylinder. Y squared plus z squared equals 36, where z is greater than or equal to 0. X is between 3 and 5. And f of xy equals z. So once again, it's just the positive square root of 36 minus y squared. Now the x partial will be 0 because there's no x there. The y partial, you bring down the 1/2, and I kind of skipped a step here, but there would have been a negative 2y there, and the 1/2 would have canceled the 2 and just left the negative y right there. And of course, this becomes negative 1/2. So your radical becomes 1 plus 0 plus this term right here squared, which I'll drop it into a fraction here in this step right there, but I left it like this. So it's going to be y squared over 36 minus y squared, which you can see I did my typical common denominator thing again. The y squareds cancel. So you have 6 over 36 minus y squared. dA, which I haven't decided what path I'm going to take yet. You know, path, in other words, not path like in a curve or something, you know, parametric. I mean, am I going to go rectangular, polar? What am I going to do? But first thing, I want to resolve all this business first here. So we know that, so the function we're integrating is z, and we already know what z is. Z is this right here, square root of 36 minus y squared. So that is our z, and this is what we just found right here. And that cancels out. Now I'm going to go dy dx because I don't need to go polar here. It's not that complicated, really. It works out, and the trickiest part, I think, at this step is coming up with the limits of integration for y. I mean, it might not be so obvious once you see how I do it. All right, so we're mapping this down to the xy plane. So there's your x from 3 to 5, but it tells you nothing about y. So what we have to do in the xy plane, we go with the fact that z would be 0, and you're just solving y squared equals 36, and therefore y would be plus and minus 6. So that's not easy to see, but now that you've seen it, hopefully that will be all right. So those are going to be my limits of integration for y. They're going to be plus, minus 6, and positive 6. So this is really easy. We're just integrating 6 dy dx, negative 6 to 6, 3 to 5. I'm not even going to go through that. That's so easy. Equals 144. Did that one of the ones have the answer there already? Yep, 144. Hooray! Definition of the flux integral. Here we have this velocity field F indicates the direction of the fluid flow. Okay. Looks like it could have some interesting applications. There's kind of a couple of ways to do this, but I'm only going to do it one way, once again, kind of as a time saver. You do this as oriented upward or oriented downward. I'm going to just go oriented upward every time. Just keep it consistent. So here's what I'm showing you is going to go for this part for the normal vector right here. For the normal vector, essentially it's the gradient sticking out of there. But since this last term is actually z, function that is just z itself. In other words, if you put this in implicit form and brought the z or brought the gy xy, that's what I did. So if you said z minus g of xy, so you have a zx, a zy for this g actually, and then the derivative of z is 1. So just go with this. Don't worry about so much what I just, probably confusing what I just said. Because it's sort of like saying z equals z of xy. So that's going to be always negative zx, negative zy, comma 1, and then f will be whatever f is. And we'll do a dot product, and then we'll have a function to integrate. All right. Oh, there, okay, there it is in writing. So you heard me say it verbally, and there it is in writing. Well, we have a nice region of integration here. That's a good one, easy one there, automatically. Rectangle. So here's our vector field. That'll be our f. So we have to get our n. So we solve this for z, which would be 4 minus x minus y. Oh yeah, we had this one for an earlier problem before we were using vector field. The partials for zx and zy would both be negative 1 and negative 1. But the formula, or what we're using for n, is negative zx, negative zy 1. So you take the negative of those. So it's the negative of negative 1, the negative of negative 1, and 1. So it turns out the normal vector is 1, 1, 1. So now we dot our function, vector field, 3x, 3y, z, then we'll worry about substituting after we do the dot product. No point in substituting now. Let's do the dot product till we get it in scalar form, which will give me 3x plus 3y plus z. So what I have to do here, of course, is x and y are good, but we need to solve for z in terms of x and y, which we conveniently have that right here. So just replace our z, like I did right here, with 4 minus x minus y, and combine the like terms together, so you actually end up with a 2x and a 2y, so it's 4 plus 2x plus 2y. Work out the integral. And antiderivative makes it 4y. This will be 2xy. That'll be y squared because of the 2 in front. And from 0 to 2, so I plug those in for y. I get 8 here. I get 4 there. That makes 12. Right here in the middle, I get put in 2 for y. I get 4x. So I have 12 plus 4x from 0 to 4. Makes that 12x plus 2x squared from 0 to 4. Plug it in right here, and we get 80. And it's 80. All right, so that will conclude this video for surface integrals in a non-parameterized form. Thank you.